Yeah.
Okay, let us begin the afternoon session. We have Professor Catherine Sulem from University of Toronto, who will speak to us about a Hamiltonian. I don't know how to pronounce that. Is it Dysthe equation for deep water gravity waves with constant vorticity? Thank you.
Thank you very much. First, I want to thank the organizers, Barbara, Gino, Mark, and Dionysis for inviting me to the workshop. And I regret I cannot be there in person. I would like to talk today about a problem related to water waves. And it concerns the water waves in a situation where there is some vorticity. And I mean, just to explain the various words in the title. So it is water waves with vorticity in a regime that is weakly nonlinear. And when one would like to approximate the solution in the form of modulated water wave train at a higher order. So I will explain. Dysthe equation is the name for a nonlinear Schrödinger equation written at a higher order. And here an effort has been done to obtain this approximate solution so that the amplitude solution remains Hamiltonian, keeps the character of the original problem. So this is, I have to go down. So as I was saying, we're going to consider the water wave problem in 2 dimensions in the presence of vorticity. So the simplest assumption that one can make is when the vorticity is not 0, is to assume that it is constant. And although, of course, it's quite a mathematical simplification, it has been observed experimentally that it is sometimes justified. This problem of the water waves with constant vorticity has a Hamiltonian formulation. It was due to Eric Wahlén and also Adrian Constantin in 2007, 2008. So I will discuss this context. And we are interested in weakly nonlinear quasi-monochromatic waves. So a situation where one develops a modulation theory. And so in this context, of course, the nonlinear Schrödinger equation, the famous approximation for the amplitude, was extended at a higher order by Dysthe. So I will in the classical problem of water waves with 0 vorticity. And our effort here has been to derive a Dysthe equation that preserve the Hamiltonian character of the original problem. Indeed, this high order nonlinear Schrödinger equations are not as generic, canonic, not as canonical as the nonlinear Schrödinger equation. So it has different forms depending on which quantity exactly you approximate. And well, we thought in this project, the effort was to keep the Hamiltonian character of the original problem. And then to finish, I will show numerical simulation to validate the approximation. So full Euler system giving us approximate numerical solutions and compare with the approximate solution through this modulated theory. We also confirm several observations concerning the effect of vorticity on modulational stability of Stokes waves. And in 2008, there was also a Dysthe equation derived in this text by Carter, Curtis, and Kalisch, and that was also a way to validate our approximation and their approximation against the Euler equation. So this work was done with my collaborators, Philippe Guyenne from Delaware University, Adi Bekkajan, he's a postdoc in Toronto, and the work will be published in Journal of Fluid Mechanics. Okay, so these first slides are really the very classical one that I just write down for the notations and so here is the water wave problem where we are interested in the evolution of the free surface over a two-dimensional fluid. And in our derivation today, we'll assume deep water. So in the classical formulation of the water wave problem, the fluid is assumed to be incompressible and also irrotational. That's an approximation that's done often in oceanography when oceanographers are particularly interested in the propagation of waves and not so much of the vorticity or vortices. And this leads to the existence of potential flow that I denote phi that satisfies the Laplace equation in the domain. And all the non-linearity is expressed through boundary conditions at the free surface. The two classical boundary conditions, kinematic and dynamic. The kinematic is essentially that the non-linear, the normal component of the velocity of the surface wave is equal to that normal component of the velocity at the surface wave of the particles. And the dynamic condition expresses the continuity of the pressure. So these are the classical equation, and it's of course well known that in '68 Sakharov observed that this system has a Hamiltonian formulation in terms of the canonical variable being eta of x being the surface elevation, and xi, that is a trace of the velocity potential. In the same very short paper of '68, Sakharov derived also the NLS equation for the amplitude. And this formulation allows to translate the original water wave problem into a problem where only the variable are surface variables, eta, the surface elevation, and the trace of the velocity potential. Now, in the case of the non-zero vorticity, which is the topics of my talk today, it is an important situation where the vorticity cannot be neglected, and in particular in the situation where there are currents and interaction between currents and wave propagations. Now, unlike the irrotational case, a full dimensional computation is necessary to solve the vorticity field. One has to couple this evolution of the surface waves to quantities inside the domain. And because of this complexity, there has been a number of models derived, in particular in the long wave regime, work by Castro and David Lann, also Richard and Sergei Gavrilyuk, where they proposed simplified models for rotational waves. Now, one situation that has attracted a lot of work is the case of constant vorticity. So when, of course, it's an important mathematical simplification. On the other hand, it can be justified at least somehow, as it was observed experimentally that waves in a regime where the waves are long compared to the depth of the water, the presence of non-zero mean vorticity is even more important than the specific distribution of the vorticity. And so mathematically, the constant vorticity corresponds to the presence of a horizontal shear flow. And this horizontal shear flow, it has a linear profile in the y direction. Now, interestingly, the character of the interaction between the wave propagation and the current depends on the direction of the vertical shear compared to that of the direction of the wave propagation. So in the literature, a current who is propagating in the direction of the propagation of the wave is called a favorable current, and in the other case it's called adverse current. And this refers to the fact that experiments and also numerical simulations have indicated that so in the case of the current of the adverse current, this adverse current will shorten the wavelength. It will increase the size of the wave, the height of the wave, and its steepness. While a favorable current, so in the propagation of the wave, will, on the contrary, increase the wavelength and flatten the wave. And so that's a very important distinction between these two situations, and several works have been done in both cases, in both situations that I will quote a few of them, a section of them. So interestingly, in the case of constant vorticity, another mathematical property that is very convenient for theoretical and also numerical studies is that it also allows a formulation of the equations only in terms of surface variable only. So here I have made a selection of works, either mathematical or numerical, concerning water waves with vorticity. This is only a selection because there has been a lot of work. So the first two concern mathematical problem, existence of surface waves with vorticity, starting with Constantin and Strauss, and with many papers of this author with different collaborators. The second paper is also a mathematical work by Berti, François Maspero, where they prove the existence of small amplitude time quasi-periodic traveling waves with constant vorticity and its bifurcation analysis. Then there is a number of work about existence and stability of these progressive periodic waves in constant vorticity, in particular Dachenko, Wheeler, and Blight-Parao. They construct exact solution mathematically and numerically, their stability, or they study their stability. Then there is also the situation where the problem is considered or in a stratified fluid with the work of Hopper, Kozdedinova, and Grimshaw, and several other papers by Karima Kozdedinova concerning interaction between internal and surface wave. This is a work about adverse current, so leading to focusing of waves. Capillarity waves also being under consideration, waves, And in terms of models, the case of the influence of vorticity, of constant vorticity for long wave models, and also on modulational instabilities of wave train, so which will indeed the case of today's presentation. The original work of Thomas Carriff-Mana for an NLS equation in this setting, and the Dysthe equation that to which we have compared our model. Okay, so after this horizon of works, I will present the governing equation, the Euler equations, the Euler system with constant vorticity. So we are in a situation where the fluid is indefinite depth, so infinite depth, h equals minus infinity, and the vorticity is assumed to be well, the vorticity in 2D is satisfied, is denoted by gamma. It's satisfied, it's conserved along the trajectories of the fluid, and if it is initially constant, it will remain constant in the two-dimensional setting. Now, unlike so we cannot define directly velocity potential, but so we introduce a stream function psi, which is defined by u, the velocity being the curl of the stream function. The stream function satisfies the Poisson problem, and from this stream function, one can easily construct an associated function that I called psi tilde, that is harmonic by modifying this stream function by an extra term, gamma y squared divided by 2. Okay, so one can associate a harmonic conjugate, and this generalized, that we call generalized potential. So it is related to the velocity, or related to the harmonic to the stream function by this relation. And we see here clearly that the presence of the constant vorticity induces an horizontal background shear flow with a linear profile. So horizontal, it modifies the velocity here the first component of the velocity, and it has a linear profile in the vertical direction. So the terminology co-propagating current, counter-propagating current, it depends a little bit of the paper. They're not all consistent, but in our setting, gamma strictly positive will correspond to a co-propagating current. It contributes positively to the velocity, and gamma negative will correspond to a counter-propagating current. Okay, so now the boundary condition, in the same way that one defined the boundary condition for zero vorticity, one writes the kinematic condition and the dynamic condition. It's a little bit longer formulas because of the presence of the vorticity, but it's exactly of the same type. And the two blue equations here, eta t dt, derivative of eta respect to t, and the evolution of phi being this generalized potential, are given with this equation here and the one below, the last line. Now, altogether, we can write the governing system, the Euler system, which is composed of the Laplace equation for this generalized potential phi, and the two boundary conditions on the evolution on the surface wave at y equals eta. we will assume that as y goes to minus infinity, so very deep in the flow, the functions phi and psi tilde, you see psi tilde appears here also, tend to 0. And so this is what I was alluding at the beginning. Wahlén and Constantine at the same time, they showed that this system has an Hamiltonian formulation in this variable eta and xi being the trace of the velocity of that general potential, general velocity potential on the surface. And they were able to write this system in the form here, d dt of eta xi equals a symplectic matrix that is not canonical, gradient h being the Hamiltonian, h being the total energy as naturally. So here, so the first observation is the system is not canonical. So I remind you that gamma is the strength of the velocity, the vorticity, dx minus 1, well, it will be defined as a primitive of the function. I will write it in a minute. The Hamiltonian is composed of several terms. So the first and the last are the one that always appear when the vorticity is 0. And the two middle terms are the additional term due to the presence of the vorticity. G of eta, here written in green, is the Dirichlet-Neumann operator that appears naturally in the problem of water waves. It expresses it's the map that associated to a Dirichlet data to the trace of a harmonic function on the surface, its normal component, and it is normalized by square root of 1 plus eta x squared. Now, moreover, it was observed in the paper of Wahlén and that under a change of variable, under this change of variable, eta xi change to, well, eta doesn't change, and xi is replaced by zeta defined as follow here. This Hamiltonian system has a canonical form, which is written here in red. And the Hamiltonian expressed in this new variable, well, is written here with this calligraphic H. It's essentially the same with xi replaced by zeta. And so the operator d minus 1 is defined as a primitive of eta, assuming that we will assume that eta tends to 0 to plus or minus infinity. And we will also assume that the integral of eta over the whole domain is 0. It will, if it's true at t equals 0, it will remain the same. Okay, so now we have a Hamiltonian system, and we can will use the theory of perturbation of Hamiltonian system in order to consider the regime and the consideration which is weakly nonlinear waves. So at the heart of this Hamiltonian perturbation methods is the fact that the Dirichlet-Neumann operator has an expansion in powers of has a convergent Taylor series near eta equals 0. And it is analytic. It goes back to the work of Kaufmann-Meyer. And not only it has a Taylor expansion that converges, but each term can be expressed relatively simply by combinations of product in the physical or Fourier space. The linear approximation in the case of the flat water at rest is The first term is absolute value of D, meaning the symbol being absolute value of K. So D is defined as 1 over I ddx. And the other terms can be expressed by formulas, or explicit formula in a recurrent way. In particular, it was very useful in numerical simulation. Associated to the Fourier expansion, to this Hamilton expansion of the Dirichlet-Neumann, there is also a expansion of the Hamiltonian, where each term is homogeneous of degree m in the variables. Now, as we are looking for weakly nonlinear waves, we will naturally need to consider the linearized water waves near equilibrium, and it is given by keeping in the Hamiltonian only the original term, the first term. I mean the first term, and then the formula a little complicated, but everything is explicit, and it is traditionally convenient to diagonalize this matrix by introducing symplectic complex coordinates that are defined in the following way. So from eta and zeta, we do this combination A of d eta plus I A minus 1 zeta, and A is the operator that consists in taking omega. So omega is the, if gamma were 0, it would be the dispersion relation, but so it's a modified dispersion relation, and A is related to omega by this formula. In any case, in this variable zeta and zeta bar complex conjugate, the Hamiltonian the Hamiltonian system is the diagonalized, and takes this form, and is in particular, so here in the first term, the quadratic term, the Hamiltonian, is expressed as the integral of omega k zk square, which is the canonical form in the variable that diagonalize the leading term in the quadratic term in the Hamiltonian. Associated to this quadratic term, there is a linear dispersion, and so we see here the linear dispersion is denoted capital omega of k. It's related, so omega of k was defined a little bit before here. It's a square root of gamma square over 4 plus gk, and it is modified again by an extra term. So the linearized system at the end becomes this one, the scalar system, a scalar equation. All right, so this is a linear problem with the linearized problem near water at rest. And a few words about modulation theory, of course, which is very topics very well known by this audience, is an effective tool to model and analyze wave in weakly nonlinear regime. So it consists in modulating monochromatic waves, or in other words, considering narrow band wave trains. And it is well known that in this regime, the amplitude satisfied a one-dimensional nonlinear Schrödinger equation, going back to Zakharov for deep water and Hashimoto Ono in 72. So a little bit after that, these papers, Dysthe proposed a nonlinear Schrödinger equation that includes higher order dispersion and higher order nonlinear term. And he wrote this equation in 2-dimension deep water. And it is written here. So the first line is our usual NLS equation. And the second line, we see that it is the higher order. There is a little epsilon, and it involves a higher order dispersion and higher order nonlinear term, that include derivative of the function A, of the amplitude. But it also includes a non-local term, a wave-induced mean flow, and that's really the signature of the Dysthe equation. This last term is defined, so the function phi here is defined as, by its derivative respect to x, involves the operator absolute value of k. So that's a non-local operator. Now, since the early work of Dysthe, this equation has been extended to many other settings: finite depth, gravity capillary waves, dispersion, exact linear dispersion, presence of dissipation, 3D-dimensional problem, and it is widely used in the water wave community because of its efficiency to describe realistic waves. And I don't know if I will have time later to show some wave tank experiments, but it has been observed in wave tank experiments that some features of the wave, like the bending of the wave, is not captured by NLS, but is captured by Dysthe. On the mathematical side, there has been several works, especially in the last couple of years, on well-posedness of this Dysthe equation. So these authors consider the Dysthe equation in 2D, so a Dysthe equation that would be derived from a 3-dimensional water wave problem. Goes back, the first results were due to Chiara about local well-posedness of classical solution in Sobolev space H3. This H3 was going down to H3 half by Koch and So, and it was done for a large class of equations. More recently, there have been 2 papers, the one by Grande, Kuryansky, and Stafilani. The first paper showing local well-posedness in H1, so going down from H3 half to H1, as well as ill-posedness for negative Sobolev, in the sense of the initial data to solution map not being C3. And simultaneously, global well-posedness and scattering for small data in L2, which in view of this previous result, to the result by Mozinka, Pillow, and So, and in view of the previous result is a sharp result. Now, this the classical Dysthe equation derived by Dysthe and by other authors for other situations was not known to be Hamiltonian. Is not known to be Hamiltonian, and so Gramstadt and Trusslen in 2011, they derived the Hamiltonian version of Dysthe, but they did not start from the original Euler equation. They started from a model that Sakharov proposed some time ago. It's called the 4-wave interaction model. And the goal of our work was to derive a Dysthe equation that preserved the Hamiltonian character of the water wave problem with vorticity, with constant vorticity, essentially from the modeling point of a numerical point of view, structural properties such as energy conservation. It's important that to the energy conservation, to have the energy conservation in our asymptotic model. And in order to compare and validate our approximation, we did the numerical simulation against the full Euler system. We also confirmed some observation about modulational stability and instability of Stokes waves, and compared to Carter-Kalisch model. So the starting point of our analysis is the Hamiltonian formulation of the equation, and the methodology is based on a sequence of canonical transformation. And by this sequence of transformation, the Hamiltonian character is automatically preserved. So now maybe I will go to a little bit more details into this derivation, which is summarized here. So the first step is to start from the Hamiltonian, from the expansion of the Hamiltonian near the still water. The tools are Birkhoff normal form transformation, that which goal is to eliminate non-resonant term, non-resonant cubic term, and this transformation is defined as an auxiliary Hamiltonian flow from this original variable to a new variable. So after this operation, the new Hamiltonian has been truncated at order 4, and the modulational ansatz, that is the approximation by slowly modulated quasi-monochromatic wave, is introduced into the Hamiltonian, and one uses homogenization techniques to identify the resonant quartic terms and to eliminate. This homogeneous technique essentially eliminate all non-resonant quartic term. Well, the final result is a Hamiltonian Dysthe equation for the wave envelope. Okay, so the first step we've seen earlier, the expansion of the Hamiltonian near the zero solution. The next step, the Birkhoff normal form. So here I have summarized, try not to go too much into calculations. Birkhoff normal form is a canonical change of variable, and we can perform it at any order. We'll do it only at order 3, and this Birkhoff normal form will transform the Hamiltonian so that only resonant terms are conserved, the others are eliminated. Now, this has been done in the context of water wave problem with zero vorticity, the classical irrotational flows, back to Dyachenko and Zakharov and Craig Wohlfork at the same time, where they carried this reduction up to m equals 4. So they eliminated all terms of degree 3 and all non-resonant terms of degree 4, and they observed for infinite depth. They observed the Hamiltonian has no 3-wave resonances, and that the remaining term of 4th order has a special integrable form. This work by Dyachenko, Zakharov, Craig Wohlfork has been used by recent work by Berti, Feola, and Pusateri And they use the integrability of the water wave system truncated at fourth order to prove rigorously a long time stability result in the following form. They assume initial condition. They started with a water wave problem, zero vorticity, deep water, with a small initial condition, periodic, in a periodic setting. And they proved, so this smallness of initial condition of order epsilon, and they proved that the solution remains smooth up to order epsilon -3. So this is essentially the setting of which we will put in place. We have been put in place for our derivation of Dysthe, and so I will not maybe go too much into these details, but so the transformation is that we will perform this third order normal form will be defined as the transformation tau will be chosen so that the new equation will remain Hamiltonian, and with we will have the elimination of the resonant term at order 3, and this transformation will be constructed as a Hamiltonian flow. So it will be an auxiliary Hamiltonian flow from time s-1 to s equals 0. So s-1 will be the old variables, and s equals 0 will be the new variables. So I will not go too much into the details because it's a little bit heavy technically, but essentially we combine two things. We combine the expansion of the Taylor series of the new Hamiltonian near this auxiliary time. It's not a time, but it's our parameter S. And we combine this Taylor series of the expansion of H prime by the expansion of our Hamiltonian in powers of the variables eta and zeta, which leads to a new expression where H prime is the new Hamiltonian in the new variable. H2 is a quadratic Hamiltonian, doesn't change. And then we have terms of various order. And the two terms in red are terms of cubic order, of third order. And the goal here is to find this auxiliary Hamiltonian K that will make the red terms, the third order terms, disappear. So essentially we have to solve an equation in terms of operators, H3 being the third order term, the cubic term in the Hamiltonian, minus a Poisson bracket of this unknown Hamiltonian K against the H2, which is the quadratic Hamiltonian, being 0. And this equation can be solved. In particular, the complex symplectic coordinate that I introduced earlier allow to solve it explicitly, because it diagonalizes this operator, the co-adjoint of H2. So I will not go too much into calculation, but the result is that in the 2D case, infinite depth and zero vorticity, this operator K3, which defines this change of variable, is very simple, happen to be very simple. It's not the case always, but in that particular case of zero vorticity, deep depth, this K3 is very simple, and it corresponds to this functional. And the Hamiltonian system associated to this to the flow is so the new coordinates are obtained as solution at s equals 0 of the system here, And because of the presence of the sign D, it's convenient to introduce the Hilbert transform. So finally, to get to the result, the Hamiltonian system that defines the third order normal form transformation, tau, that eliminates all cubic term, has the form of a coupled PDE. The first is a Burgers equation, and the second is a linearization along the Burgers flow. So that simply very simple transformation is what happens for vorticity, zero vorticity and infinite depth. Now, in the case of the presence of non-vorticity, this auxiliary Hamiltonian is much more complicated, but still it's possible to write it down. So it has a long expression, doesn't matter, but we can still compute it. And so back to our transform Hamiltonian, we have eliminated third order. We're looking what remains at fourth order. At fourth order, again, at the level of the zero vorticity, the Hamiltonian had a very simple form. So the fourth order, here it's written H plus 4. It's the old fourth order modified by a term that has exactly the same form as the old one, except that eta is replaced by its Hilbert transform. And as I say here, in the presence of constant vorticity, the formula not as simple, but the method is the same. One can calculate the Hamiltonian, the transform Hamiltonian truncated at the same at fourth order. And finally, in this H4, in this setting of new variables, one substitute the modulation on that, expand in part of epsilon, and finally, I would just write. Maybe I will go here. I will write. So the Hamiltonian can be expressed, and the Dysthe equation, the Hamiltonian Dysthe equation, for two-dimensional deep water with constant vorticity has finally the following form. So the first line, the second term here, omega, shows the wave moving at the group velocity. This blue term are the usual NLS equation, and the other terms are the additional term due to the higher order expansion. In particular, the last term in green is the non-local term of Dysthe. I will like to. So now I would like to show you. So this is the equation. It's a little bit different from the Dysthe equation that is non-Hamiltonian. In particular, it has one term less. But as several of our numerical simulation has showed, not only for constant vorticity, but other situation of 3D problems, for example, the two versions of Dysthe give good approximation compared to the waves, into the integration of numerical simulation of the original Euler problem. The Hamiltonian one having the advantage of conserving the energy. So here, the validation of the approximation. So first we examine the effect of vorticity on modulation and instabilities of wave packet. So it has the sign and also the amplitude of this vorticity has an influence of the Benjamin field instability. So here we have two pictures. The left is gamma negative. So gamma negative is a counter propagating shear flow. it tends to enhance the instability by amplifying the growth rate and enlarging the instability region to higher sideband wave numbers. So as we look here, the red line is the region, so the modulation on instability for gamma negative, and as we are increasing the size of gamma, we are expanding the curve. So as gamma gets larger and larger on the negative side, the region increases. So it amplifies the growth rate. On the other side is the gamma positive co-propagating stabilizing effect of the vorticity of the shear flow. So now the red curve is gamma equals 0, and we increase as we increase the gamma in amplitude in size. So we're going downstairs, get down the shrinking curves, increasing gamma. Okay, so here, in fact, is the plot of the growth rate against the wave number, and we see that for if gamma is sufficiently large, the instability does not happen anymore. So gamma, the red curve again is gamma equals 0. And so the co-propagating current has a stabilizing effect. And this picture shows a comparison of the surface wave elevation. So the parameter is gamma equals -2. So it's a counter propagating an adverse current. And we are comparing the prediction of the surface elevation from the Dysthe model, reconstructing from this slowly modulated wave train, and the full Euler system at 3. So the blue curve is the Dysthe, and the black curve is the Euler equation, full nonlinear Euler. And we see at 3 different times. The first picture, early stage of the Benjamin field. Later, the time of maximum wave growth. So see the calculation, I mean, the approximation is relatively good, pretty good. And the later time where we are at the end of the quasi-recurrent cycle of the modulation and demodulation. So I will essentially, I will add one more, yes, that's about the surface reconstruction. So to be able to compare the constructed wave against the Euler, the true solution of the Euler problem, one has to undo the change of variable that we did through this normal form. So through the surface reconstruction. So in classical modulation theory, the reconstruction is done perturbatively by an ansatz similar to the Stokes expansion, by adding higher harmonics to the wave spectrum. In our case, the reconstruction is done by inverting the transformation associated to the third order normal form and the modulation ansatz. So it's not a perturbative calculation. It's it just invert transformations. So I will skip this discussion about test again lab experiment, except that I would like to say that two things. That to test the Dysthe equation against lab, one has to write what's a version that is of Dysthe that is called spatial Dysthe, where the role of x and t are modified, are exchanged, because the x is acting like a time-like variable for the wave propagation of the wave tank. There are some wave gauge placed at fixed locations. And one interesting observation from experiment from Keller and Su in '82 that are also considered as benchmark for comparison is that the slow evolution of deep water waves exhibit certain asymmetric features that have the form that the initially symmetric wave packet with sufficiently large wave slope tends to lean forward. And this is essentially can be observed, can be captured by Dysthe equation, but not seeing the cubic. And there were indeed the numerical simulation of Low and May in '85 that captured this calculation. So, and we also derived. So I'm just showing the pictures here. They are red curve and blue curve that we don't see. The red and blue and curve are both versions of Dysthe. One is Hamiltonian, one is not Hamiltonian, and the dots are experiment of Keller and Su. And so the blue and red are essentially, the blue is the Hamiltonian, it's our version. The red is that of Low and May. So they coincide pretty well. And we see that the bending of the curve. So I will not go too much on that, but I will just say one word about our current work. It's related to these recent experimental studies of various authors, Toffoli and collaborators, and also Steele and collaborators, about waves in the presence of currents. So this one is rogue waves in opposite currents, where they produce experimental study of these deterministic and stochastic wave trains. And the second is also an experimental study in constant vorticity current. And we just to validate our model again, would be interesting to produce a special Hamiltonian Dysthe equation that will be appropriate for comparison with these experimental studies. And I think at this stage, I will thank you for your attention.
Thank you very much. Any questions?
Thank you.
Okay.
Catherine, nice work. I have a couple of questions to better understand your results. First question is somewhat simple, maybe not so easy to answer. So do you have numerical indication that your new version, Hamiltonian version of this equation works better compared to full Euler? I mean, no vorticity is that, or it's still in progress?
So is it Pavel? I recognize.
Yeah,
I think
this is me.
Okay, hi Pavel. So you are asking about the problem with vorticity or without vorticity?
No vorticity, even. Yeah.
So no vorticity, yes. So previously, I did not talk about that, but we have some work of the derivation of the Hamiltonian Dysthe. So we had numerical simulation of the Euler 3D. So that was the calculation of Philippe Guyenne with his code of 2D and 3D Euler, and we compared the solution of the Euler equation with the predicted approximated solution from a Hamiltonian Dysthe. So I should say I can send you, Pavel, the original paper where there are curves that show how these three calculations fit. Overall, the Dysthe and the Hamiltonian and non-Hamiltonian fit pretty well. Sometimes you could say that the Hamiltonian is a little bit better, but overall it's a good way to validate the two models. They are relatively as good, each of them, compared to the original, to the full Euler problem in 2D and in 3D.
Yeah, I see. I think, of course, Hamiltonian, version should normally work better. Okay,
a tiny bit better. Yeah, a tiny bit better when the solution, for example, if you want to calculate, I can send you the paper with a bit more precise statement. But if you calculate, for example, the error on the energy and on the conservation of energy, of course, the Hamiltonian conserves better.
Yeah, and second question, it's maybe very general. So Zakharov originally, he removed non-resonant terms somewhere, I even forget when, somewhere beginning of 70s. And then also...
I think it was Kravitsky who modified a little bit of Sakharov's.
So yeah, let me finish my question. And when somewhere like last 10 years, 10 plus years with Dichenko Senior, I think we did some work because the result was some freedom when doing this canonical transformation to removing non-resonant terms to basically modify fourth order terms. Is that, I guess you're doing something in that sense, just somewhat simplifying fourth order terms in Hamiltonian. Do I understand correctly?
Yes,
I think big freedom because you can remove third order terms, yeah, but when you're removing, you really can do different version of fourth order terms. Is that something like what you're doing here?
Well, we remove all non-resonant terms, but I know that you and Zakharov and with your group had what you call the compact equation.
Yeah, it was not me. It
we don't
Zakharov, yeah.
Right, and then we don't compare against your equation, which is a little bit different from ours. That's right.
Yeah, because it's interesting, which are more efficient. Yeah. Okay, thank you.
It might be, it might keep a better approximation, but we have not.
Yeah, I think it's interesting. It would be interesting to compare.
Interesting to compare the models. Yes.
Thank you.
I think we have a question from Peter online. Peter, do you want to unmute yourself and read your question?
Hi, Catherine. Nice talk. I just wanted to know if your mathematical prediction of the missing modulational instability, once you have the correct direction of flow below the surface, has a physical interpretation.
What exactly has a physical interpretation?
So, you showed us that that when gamma has the correct sign and is big enough, I can't remember which way it was, that indicated that the fluid flow below the surface was going either with the waves or against the waves. I can't remember. Yeah, this picture right here. If it was big enough, then the modulational instability disappeared, right?
Yes.
Yeah. So I'm just wondering if there's if you can explain that in a physical way, like why the fluid flow below the surface, far below the surface, is what I gathered it meant, is affecting the instability of the surface waves.
Well, it's not far below. I mean, we consider the fluid infinite depth because of mathematical convenience, in sense, because essentially that the wavelength is much smaller than the depth, but the shear flow is below the surface, right? That's when it's active. Well, I think intuitively, if the current goes with the propagation, it somehow helps the propagation. But when, especially in the other direction, when it goes the adverse wave, so it goes against the propagation, people have seen, for example, in some papers, they see that the adverse shear flow can block the wave, essentially, because it goes the other direction, and then so first it blocks the wave, and then they see strong increase in steepness, and then they see wave breaking. So I think that was what in one of the papers that I quoted in the beginning about focusing waves and adverse, that's what they claim.
I see. Thank you.
Any other questions?
Can I ask a quick question? Jenna?
Yes, hi, Karima.
Hi, Catherine. Thank you for a nice talk. Catherine, in your overview, you've mentioned homogenization, some kind of homogenization, but in your talk, you skipped over that. Can you please say a couple of words? What did you mean by that?
Yes, well, I meant that, if I may have something here written. Yes, homogenization. Essentially, in this Hamiltonian, you have integrals. And in these integrals, you have functions that depend on the long wave and then these fast oscillating terms. So essentially, the fast oscillating terms, they compensate each other. They multiply each other, and they are effective only if all the oscillation cancels out.
Okay.
And there is a I can send you once later a paper that expresses that a little bit more mathematically. If you have an integral of a function, let's say of epsilon x multiplied by g of x over epsilon, so a product of a fast oscillating function and a periodic fast oscillating and a slow, essentially what counts is only the average value of fast oscillating. So because here the average value, the fast oscillating exponential ikx, the average value will be 0.
Okay.
So that's essentially that, the product of fast oscillating and smooth.
Thank you. And another quick question. You know, for extended KdV equation, for example, there are so-called near identity transformations introduced by Yuji Kadama and then developed by Focus and Liu, which map extended KdV to itself. And these near identity transformations can be used to find a Hamiltonian version of extended KdV. Is there something like that for this equation?
Well, you know, I think Karima, I think you told me that earlier in July, and I don't know.
Okay,
But maybe,
because it's also not an asymptotically exact equation. Yeah, so probably.
Yes, I think I should look into that. It might be of interest to compare and to see what this transformation would give us.
Okay, thank you.
Thank you.
Thank you. Let's thank our speaker again.
Thank you very much. Thank you. Thank you.
Thank you very much, everyone.
Thank you very much, man.
Thank you.
Thank you.
Stop.